Alrighty, so we're going to look at these intermolecular forces. We already did that little activity and watched the little video snippet about the fantastic power of intermolecular forces helping the gecko climb smooth surfaces. But right now we're going to look at intermolecular forces and pretty much their effect on liquids. Because if you remember back from our study of gases, that there really aren't any major intermolecular forces under the conditions that we typically look at. We solved problems using Pivnert, our ideal gas law, and then we also looked at using the van der Waals equation. And when we did that, we saw hardly any difference at all, even though that equation compensated for the volume of the particles and the intermolecular forces between the gas particles. So we just pretty much can ignore them when we're talking about gases. And solids, the particles are in a rigid structure, so they're already locked into place and are vibrating, so there's really not a big need to talk about the intermolecular forces with our solids. But with our liquids, we can see some different properties that arise. First off, surface tension. And of course, we'll look at our favorite liquid, water. And if you've seen little water bugs crawling across the water, you can see like their feet actually push down, make a little dimple in the water. When you have water molecules or any liquid, when you're looking at the particles in the center of the liquid, they're attracted from all around. The ones at the surface, however, are only attracted to the molecules that are beneath it. They're not attracted to the air above. And so there's like this inward pull, and that is what creates our surface tension on the top. So the stronger those attractions between particles, the better the surface tension will be. And water has some pretty strong intermolecular forces, which is why it has a pretty high surface tension. If you've ever belly smacked off of a diving board, then you've experienced the intermolecular forces. You've experienced that water surface tension. If you're coming from a pretty high height and you smack on the surface of the water, it hurts, which is why if you watch any upper echelon diving competitions, they typically run bubblers. And what that does is it helps to break the surface tension of the water, so if you land awkwardly, it hurts less. Still hurts, a little less. And I'm sure perhaps you've seen some beads of water on a freshly waxed car or on a plant, and you can see in this diagram again what I was mentioning is that if you're a particle in the middle of the liquid, then you've got attractions all around. But the ones at the surface only have the attractions inward, and thus the surface tension exists. As it says there, there's a tendency for the surface area of a liquid to be reduced as much as possible, which is why we see spherical raindrops. Because if you remember from geometry class, our sphere has the smallest surface area for a given volume of any geometrical shape. I'm sure you remember that. But it can be measured, okay? So in our textbook or in charts, you can see typically some measurement of the surface tension as you see here. It's measured as the energy required to increase the surface area of a liquid by a unit amount. So like in our book, joules per meter squared, that means, how much energy does it take to increase the surface area of a liquid by a meter squared. And so again, the higher the surface tension, the stronger the intermolecular forces, because we have a much greater linkage of those particles both inward and on top of the surface. Another interesting fact is this, or property, is capillary rise. If you've used capillary tubes, or anytime we typically use glassware and we have water in it, you see our good friend the meniscus. And this is happening because of the fact that water molecules are attracted to the glass. And so they get pulled upwards and are attracted to the silicon dioxide in the glass. Mercury is not attracted. So if you've seen a thermometer, a mercury thermometer, or an old-time blood pressure device, then as the mercury is going up those tubes, you see the rounded top because it's not attracted to the glass. So you see a dipping based on some other factors, but you don't see the meniscus as we do with water, since there is that intermolecular attraction. Viscosity. Viscosity is basically talked about as the resistance of a liquid to flowing, and we can have more viscous and less viscous fluids. Water is not very viscous. Syrup, for example, is very viscous. And so, based on the, again, intermolecular attractions, when they are weaker, then the liquid will flow a lot easier. Viscosity is also affected by temperature. If you've ever taken syrup out of the cabinet and poured it onto your pancakes, it flows a lot slower than if you put it in the microwave first, heat it up, and then pour it. It would pour a lot faster. Motor oil. Most of our standard cars, when you get your oil changed, they're putting in SAE 10W40 motor oil. And basically what that's saying is that it'll have different properties in the winter and summer. Okay, when you're operating your car, like around Cleveland, Ohio, in the cold, cold winter, the motor oil could become very, very viscous and wouldn't do its job in your engine. And so the oil that is used now is created to maintain the viscosity in temperature extremes. So when it's really, really cold or really, really warm in the summer, then the viscosity will maintain and stay consistent in order for our cars to operate better. Alright, so looking at these intermolecular forces and the explaining liquid properties, it doesn't take a genius to figure out that our definition here is that they are the forces of interaction between molecules. And we have two main divisions, van der Waals forces and hydrogen bonding. Within van der Waals forces, you may hear talking about dipole-dipole interaction and London dispersion forces. So let's take a look first at some of our van der Waals. And so you see here, it is an intermolecular attraction, so in order to break it, it's going to take some energy. And so typically we see that our van der Waals forces have somewhere between 0.1 and 10 kilojoules per mole as far as quote-unquote bond energy is concerned. And you can see compared to 40 to 4,000 for most of our covalent and ionic bonds. So not as strong as even our weakest covalent bonds, but again, the power of intermolecular forces can come from, like we looked at with the gecko, lots and lots and lots of them adding up together. Alright, so let's first look at our dipole-dipole forces. Now this is only happening with polar molecules, and of course when we have a dipole moment, then we'll end up having a partially positive and partially negative side to each molecule. So in hydrogen chloride, for example, HCl, not hydrochloric acid here, that's a solution, just pure hydrogen chloride, there would be a dipole moment going towards the chlorine atom. And so the hydrogen side of the molecule is partially positive, the chloride side is partially negative. So when you have a bunch of them together, then you have those interactions that you see over here as dipole-dipole interactions between the partially positive and partially negative sections of that molecule. And this has an effect on a liquid's boiling point. So hydrogen chloride you see here boils at negative 85 degrees Celsius, compared to neon, which boils at negative 246, a huge difference. And that's because neon simply has London dispersion forces. Again, you have to remember that our electrons in atoms or molecules are mobile. They're moving around in their electron cloud. So when I have atoms, those electrons, like you see here in this picture for neon, are swarming around. And they can be caught on one side of the atom more than another, and this happens all the time. And you can see that little miniature dipoles start popping up. Now, more electrons, the bigger those dipoles are. So we're going to see the fact that London dispersion forces are tied in with molecular mass. So a larger molecule has more electrons moving around, and we end up creating greater London dispersion forces. So here you see like the fractional distillation of crude oil. These smaller compounds, like 3 carbon chains, have a boiling point of 25 degrees Celsius or so. A larger carbon chain, like a 20 carbon chain, 340 degrees Celsius. Over 40 carbons, we're looking at over 400 degrees. So you can see the larger the molecule, that would mean the London dispersion forces are greater, holding those molecules closer together. So it's going to take more energy to break those IMFs and allow those molecules to vaporize. Same thing here we see with simple elements and just atoms, our noble gases, helium, neon, argon, krypton, and xenon. Obviously, their molecular masses are increasing, so are the number of electrons in each atom. So again, when we see this shifting of the electrons in the electron cloud, then the interactions will be greater because the little poles that are developing are that much stronger. And so you can see a significant increase in the boiling points for these elements based on the fact that they're larger, having more electrons, that makes them what we call more polarizable. Okay, this is a word we'll use, and we'll see it here in a second. More polarizable. More electrons makes the molecule or atom more polarizable. Now do note down here, these temperatures are in Kelvin. So you're like, what? Xenon boils at 165 Kelvin. That's significantly still below zero on the Celsius scale. So here's an interesting situation. Here I have isomers of pentane. All of these molecules are C5H12, which means they have a molar mass of 72 grams per mole. So we would think they should have similar boiling points since they all have the same molar mass. But you can see regular pentane, which is a 5-carbon chain molecule, boils at 36.1 degrees Celsius. Isopentane, which has 4 carbons in a row and a branch, is 27.9. And then neopentane, 3 carbons with 2 branches, 9.5 degrees Celsius. What is going on here? And as you see, different arrangement of atoms causes this. When your molecule is more compact, it is less, that word we just used, polarizable. Okay, we don't see as big of dipoles forming, those instantaneous dipoles forming, when the molecules are more compact. Because of this then, less London forces, and because of that then, we would have a decrease in the boiling point. EP exam loves to use this. They might put a couple different molecules and say, you know, why are the boiling points so different? So again, this is when we're talking about isomers. We have all 3 C5H12s, and we can see the difference in boiling point because of the polarizable factor. Look here though. Here I have 2 molecules, CH3F and CH3OH. Their molar masses, very, very similar. They're both polar, or they both have, yes, they're both polar molecules. They have dipole moments, and you can measure dipole moments in a machine with a magnetic field. And when you look at that, I see that 1.8 versus 1.7, not a big deal. Boiling point, big deal. WTF. What's that force? See what I did there? Pretty cool, I know. And this force is something called hydrogen bonding, which is the king of the intermolecular forces, and that'll be the topic of our next little video here. Alright, hope this part has helped so far. See you soon.